Okay, for one announcement. The exam is going to be on the week starting with March 30th. And the exam might be either on Tuesday or Thursday. Thursday, we have only 1 hour. And I think some people here had another course after this. You had, I think, on Thursday. Am I right? Or did you drop that course?
I think you're right.
Okay, now why don't we check with that, because I may prefer to do the exam on Thursday, or we are going to do the exam sort of like an evening, which means that we are not going to do lectures that day, okay? I may skip doing the exam very early in the morning. Okay, now today what I'm planning to do is as follows. We have 2 papers that we want to discuss for network location problem in supply chains. Now, both of these examples are interesting in the sense that they add on the classical location problem. Now, how many of you are familiar with the classical location problem? Have you? Classical location problem, like the integer programming problem, where the binary integer programming problem, where you try to locate the facility somewhere, you minimize an objective function, facility location problem. You might be familiar with that because you have seen the formulation. Some of you may know it a little bit in more detail. But what we're going to see here is we will try to combine those efforts with certain costs which are specific to the supply chain structure. In one case, we're going to call it the inventory cost. In another case, we're going to call it the waiting cost or the dwell cost. But basically, we will try to incorporate that. You're going to see that it's not going to be very standard. You need to do something additional at the top of that. But once you are there, of course, you can use the theory which is behind facility location problems. Now, the first paper that we're going to see is by Nozick and Turnquist. 2001, and actually it is a follow-up paper that they have, so it's not only the first one. That's the reason why within the paper, if you read the paper in sections 2 and 3, they refer to another paper by themselves, where they actually deal with certain things that they refer here. Now, the question here is basically the following. We have the location selection problem for a distribution system. Basically, we want to select distribution centers, and I'm going to call it DCs. Sometimes in the paper it's called RDCs. In some figures, it's the same thing. Either regional distribution centers or distribution centers. So the question is, how am I going to select my distribution center so that I will probably balance certain cost factors and service factors that are indeed there? Now, we know that there are a number of issues that we can include in this, but in this paper we are only going to see 3 issues. And the first issue would be the inventory costs. Now, if you recall from a previous paper that we discussed by IE-571, we know that if we create a more central system, the inventory costs will be less. Now, what do we mean by that? Well, if you are given a choice, you are going to distribute everything with respect to inventory costs, of course. You are going to distribute everything from the factory. Now, second best is to have 1 distribution center. Third best is to have 2 distribution centers. In other words, we know that from Eppen's paper, you want to centralize everything because of the variability of demand, lead time demand that you see. If you pool everything together, you are going to have the least amount of total inventory in the system. Okay, so on one side we are going to have inventory costs, which is against actually having distribution centers. The second one is going to be transportation cost. Of course, transportation costs should be computed properly, which means that it should include mode selection problem and so on if available. Now, in this case, we don't have that. We only have one mode where depending on, and the cost depends on the distance. Okay, very simple. Actually, this paper is very simplistic. Some of you may even say that, well, I mean, this is too simple to manage, which is correct partially, but I think it is nice that it takes some costs into account, or at least tries to do that. Okay, now the third one is the so-called service quality, where we don't know how to measure the service quality yet, but we are going to measure it with the proximity to customers. Proximity of the DCs, of course, to customers. What do we mean by proximity? Well, if the distance between the center of customers and this DC or RDC is close enough, then we say that this RDC can give service. For example, IKEA, we don't have any IKEA in Ankara, but if we had one, let's say in Sivrihisar, okay, which is 150 kilometers away, well, it might be worthwhile going there, like you're gonna simply drive there one day. It will take an hour and 20 minutes, buy certain things there and come back, okay? Whereas if the closest one is in Izmit, which takes 3.5 hours, then this is too far away. Now, similarly, when we're talking about distribution systems, the retail stores are the customers. Okay? In this case, they are talking about an automobile distribution system, which means that the dealers are the customers. So you have certain dealer locations, and if the location of the DC is close enough to the dealer, it means that you can ship an automobile or a number of automobiles in the same day. You ship it early in the morning, it is going to get there in the afternoon, which means that if somebody ordered, we'll get it next day. Okay? So this is the definition of service. Definition of service will be different in different contexts. For example, if you are distributing blood, okay, which is very important, like your retailers then will be the hospitals which are requiring the blood, and you're a blood bank, then the proximity is again going to be extremely important because of the urgency that you need the blood. Okay? So in that respect, the service quality is a function of the proximity, and in this case it is taken as 0,1, which means that if it is a certain distance away from the retail store, then we call it that you give 100% service. Otherwise, you say that it's 0. Okay? So this is basically the way that it's defined here. Of course, you can give a cost to that rather than doing this, and we're going to talk about that later once we finish the paper. So proximity to customers or demand points is the way that we defined service quality. Now, the classical problem is, of course, you have a plant here. Okay? Usually we show plants with triangles, meaning that there is some kind of a manufacturing going on. And then you have sort of DCs, which are served by the plant. So in this case, we assume that there is a single plant. So we have some DCs which are served. Each DC has its own region. So here, what we have is we have customer points. But the question is, we don't know which customer point is going to serve by which DC, because that depends on the DCs that will be open. Let's say that these are this is sort of the typical picture that we have at the end. But in general, when we are solving a problem like this, we have alternative locations for DCs. So in this case, let's assume that we have J. J stand for the DC locations, and let's say that we have capital J of them. So there are capital J location possibilities for which we can put our DC. Okay? And depending on the cost, we are going to open some of them. Okay? And depending on the ones which are open, the customers are going to be assigned to them. Now, how are we going to assign the customers? The result is obvious. We don't have any capacity constraints in this paper. So it means that the one which is closest to the customer that we're talking about is going to pick up that customer. So as you can see now, as you differentiate the number of DCs that you open, if you change that number, the assignment is going to be different. So the safety stock requirements that you are going to have for the different DCs are going to be different because of the different assignments. Now, this is not a very straightforward problem if you really want to take the inventory cost into account. Okay? So this is actually the structure. Now, if you remember in the centralization problem, even if we assume that all the customer points have equal demand, okay, with the same sigma and mu, remember the EPAM paper, the safety stock that you keep here in order to serve those customers is not a linear function of the variance, but it is basically square root of n is the factor that we remember, we have, if you recall. If you recall, when we have complete centralization, square root of n, where n is the number of customer points, times sigma is going to be the determinant for the safety factor in this DC. So here what you have is you have square root of n versus, okay, all the binary terms that you have here. To open DC, you have 0 ones, so on and so forth. So you have nonlinear binary programming problem. In general, if you reflect it, even when you have the customer points identical, it's going to be a very hard problem to solve. So here, what we are going to do, or what they propose is, what Nozick and Turnquist propose is very straightforward. They are going to have some kind of an approximation for this cost, and they will devise a certain way of putting this cost into the location problem in a certain straightforward manner, once they have this approximation. Okay? Now, any questions on the difficulty? Why this problem is difficult? Should I describe it again? Okay. Okay. Now, once we have this, then the next step will be, well, we have to find a way to model the inventory cost. The way that they model the inventory cost is in the previous work, and it is based on a number of assumptions. Actually, the inventory model that they use does not fit this specific environment. And, well, you have to stretch a little bit to fit it to this environment. Nevertheless, it's an approach, and I'm going to talk about that. Basically, what they do is the following. They assume that a customer point, the demand at a customer point I is going to be a Poisson distributed random variable with parameter lambda I. Well, when you are distributing automobiles, this is not a bad assumption. Now, usually you can say this in the following way as well. The unit that we are talking about, the unit of demand, may not necessarily be one automobile. Okay? Now, they don't explain it there, but in the other paper they talk about that. The unit might be, let's say, a truckload of automobiles. Usually trucks which carry automobiles, which transport automobiles, are going to take eight automobiles. So, for example, this might be one measure that they use. Now, if they use this measure, this is going to be reasonable because of the reasons that I will explain. So, you can play with the unit of demand, of course, in the way that you want. Okay, it's not going to change anything. You aggregate demand. You usually don't disaggregate the demand because it's going to create more problems, but you usually aggregate the demand. It only goes one way. Okay, so in this case, this is the assumption. Now we assume independent, identically distributed demand for each of them, which might not be very true. We know that if you have one car dealer in Aydınlık, another car dealer in Dikmen, okay, their demand may not be independent because we're talking about a large city, and if you really don't like the colors that you see in Aydınlık, you're going to go to Dikmen to buy another automobile. So I expect that their demand should be sort of dependent, but again, it depends on how the customer points are defined. Okay? So if you define, let's say, 3 customer points in Ankara only, then it might be independent, of course. But if you define all the car dealers in Ankara, okay, for a certain brand, sometimes you have like 25 of them selling in Ankara. Then you're going to have some dependency. But let's assume that it's independent. So if it is independent, what we have is, remember from your stochastic courses, is that if you have different Poisson streams coming in, what will be the sum of that stream? It will again be Poisson, superposition of Poisson processes, and it will be again Poisson. So they define capital lambda as sum I from 1 to n of lambda I. Now, what is the use of this capital lambda? Of course, as we are going to bring n of these customer points together, we're going to have this demand. So this demand observed by the DC. So what we are going to do is we are going to model the DC inventory level in order to come up with the DC inventory cost. Okay, this is what they have been doing in the other paper. So they define this in this way, and then they make the following assumption. They assume that they apply S-1 S policy at the DC. Okay, what is the meaning of S-1 S policy? It means that whenever a customer point asks for a unit, okay, the DC orders the plant that unit. Okay, that's the meaning of that. Like every time that you have a demand going out, remember in general we call it little s, capital S, but if the little s, lowercase s value is capital S minus 1, what is going to be the result? Well, every time that you have a demand coming in, you're going to give an order. Okay? Now, this is reasonable up to a certain extent with the explanation that I had. If your unit of demand is 8, then this is reasonable. Why? Because then this is the meaning. If there is a demand from a customer point, it means that they are going to use those trucks to ship it, 8 of them together. And once 8 cars are gone from the DC, the DC is going to ask the plant to ship 8 units. It's reasonable, okay, because the same truck is going to go there. So this becomes reasonable. Now, when do you use S-1 S policies? Why do you have a policy like that? Why don't you just say that, well, I want to have batches in terms of when I'm ordering, I want to have batches rather than ordering a single unit. What's the meaning of that? When does it happen, actually? Well, yes? Well, if it is not, well, still it means that the economies of scale in ordering is such that, okay, the fixed cost is very little. The unit cost is very high. Rather than keeping it in the inventory, you prefer to give order continuously. So when will it happen? If the item cost is very expensive, this will happen. Okay, because the inventory carrying cost will be very high. Rather than carrying inventory, you prefer to give the ordering cost every time that you order. Okay, so what are the examples for that? Well, planes. Okay, let's start with that. Okay, you are not going to order a batch of planes because it's already very expensive and it's not meaningful to do that. Okay, so in this case, this policy makes some sense, but still we know that in practice the shipment is going to be in using those trucks. So I would expect that 8 units would be a good batch size that they should use. But still you can play with it. So it's not a very bad assumption, but you have to think about it and understand that it's not applicable when you are shipping tomatoes. Okay? So in the retail, if you are setting up the distribution system for tomatoes, this is not going to work, of course. Okay. Because the tomatoes are going to be cheap. Although I know that, like, if you order a lot of tomatoes, you're going to have some loss because tomatoes are going to press each other and you're going to have very nice tomato paste. But still, I mean, you are not going to order, let's say, 1 unit. If that unit is a truckload, might be 1 unit, of course. Okay. But this is the policy that they use at the DC. Again, this is the other paper. And then what they do is they refer to a result by Feeney and Sherbrooke, which goes all the way back to 1966. It's one of the basic works that I have utilized in my PhD thesis back 30 years ago. Okay, so this is Feeney and Sherbrooke, and we're going to see a paper by Sherbrooke which uses the same property. We're going to see why this is actually a very important result. It's a very simple, intuitive result, but it's very important. Well, I shouldn't say it's very intuitive. Okay. Now, what that result simply tells us is, well, I will explain that when I introduce the term that they have for this case. Okay. Let us say that we are interested for the DC probability that. Okay, now I am sort of considering a certain service measure for the DC. Now, when I am operating the DC for n demand points, which are not necessarily identical, okay, what I'm expecting to do is I want to set my base stock level S at a certain level so that the probability of demand exceeding that base stock level, which is inventory position, should be smaller than a certain number. Okay, so this is going to be the service level. Now, for those of you who are familiar with Silver's notation, this means that we're talking about type 1 customers, type 1 service. Okay, if you are not familiar with that, then this is basically the probability of stock out. Okay, so what is the probability of stock out? Probability of stock out is probability that M is greater than S. They use this notation, which is not very, very nice. Actually, we usually use capital letters for random variables, but they don't use here. So M denotes the demand. So probability that demand is larger than S. What is S? S is the inventory position that you have in this system. In other words, every time that a demand comes, you give an order. The order is outstanding, of course. It takes some time for the order to come. So S means that we have the inventory position. But still, M being greater than the inventory position means that we should be concerned with the time that it takes for the plant to satisfy the demand of the DC. So what is this probability? This probability is given by the complementary cumulative of a certain Poisson distribution. Okay, now let's write that Poisson distribution. K is S plus 1 to infinity. This is the probability that this Poisson distribution is looking for the values which are exceeding S. And then we have e to the power minus lambda mu. Okay, well, capital lambda mu to the power k divided by k factorial. Where we know everything. This is capital lambda is defined there. Okay, and mu is, Okay, that's the expected delay or expected delivery time, excuse me, expected delivery time to DC. So here, as you see, now let's say that the delivery time was constant, okay? In other words, five time units, 5 days from the DC. So what we would be interested would be the demand during those 5 days. This is the lead time demand. This is a continuous review system. So our response time is the delivery time, lead time. So I would be interested in the demand during lead time. This is actually demand during lead time exceeding capital S. Okay, very simple actually. So it's very reasonable. But in this case, mu is the expected delivery time. And mu has a distribution. It has a variance, so on and so forth. But it turns out that the result of Finch and Sherbrooke is simply, it says that if you have Poisson distributed demand independent of each other, you have the demand independent from one period to the other, then this term, the probability of stockout term, is only a function of the expected delivery time, regardless the distribution of the delivery time. This is basically a property of Poisson distribution that makes it happen. You have this memorylessness, and memorylessness really helps you in this answer. Actually, the proof is that way. You use the memorylessness property of the exponential distribution, which is basically the image of the Poisson process, the time between arrivals. Okay? So basically, this is a result that we would understand if mu was a constant, but now it is the expected value of a distribution. So this is the result. They use this result. Okay. Now you can say that they could have assumed that the delivery time would be constant, but can you imagine that this delivery time is going to be constant? Probably not, because we are having a plant here. You have different orders coming in. Okay. There will always be some delays. Now we're going to see how we are going to analyze this in another paper by Sherbrooke. It's one of the basic papers that I want to go through for this course, and we are going to see that there. But this is the term that they come up for the inventory. Of course, when you require this probability to be less than a certain number, then you can select the S accordingly. So you are, for example, you say that this probability should be less than, let's say, R, which is 0.05. Then in that case, you find the corresponding SR value, okay? Which is basically you evaluate this. Now, of course, you have to be very careful. You can only evaluate this if you know the N's that goes here, the number of retailers the number of customer points that goes into this computation. Okay. Now, any questions up to this point? Now, next step is, of course, the following. They use their previous work. Now, what they do is they make a number of computations for equal, for customer points that are more or less equal in size. What does that mean? It means that they have identical expected values of demand. So they make some analysis previously, which result in the following, which is going to be important in this application. Now, you compute, for example, they take R to be equal to 0.05. Then they compute the S values for various different combinations of retailers. Okay? Now, and if the size of the retailers are identical, then they have this figure 3, if you have it in front of you. I'll just show the figure 3 of the paper. They make a lot of computations with different number of retailers, okay? And they come up with the total inventory cost, which is the cost which is related to keeping this S. And then they show that it's almost linear. They use those numbers, do a regression, linear regression, obtain a relationship, okay? So this is a little bit flaky, of course. I mean, I am not going to basically do all my analysis related to that. But what it means is we know that we have the square root relationship. So what we are doing is we are sort of using a linear approximation of that square root. This is more or less what's happening. So when do you think the linear approximation is going to be good? Well, first of all, you have to be in a certain region. So this is the square root function. Okay? So for example, if we have n here, this is more or less the square root function. Okay? Now, what will be a good approximation? Well, for small values of n, the approximation is not going to be good because you have sort of a very steep decrease. You start with large values and it's 1 here and then it starts to drop. But if you look at values in between, let's say 5 and 50 or 15 and 50, you're going to see that you can approximate this with a linear function. Actually, this is what they have done. They said that we can approximate this using some numerical analysis. They described that in the paper, which is straightforward. And what they do is actually they compute the actual cost. They regress that actual cost using simple linear regression. Now, as a result, what they obtain is a relationship. Well, they do some tricks, actually. They divide all the demand points into 3, depending on the demand size. And they do the regression for each of them separately, and then aggregate the regression. Okay, so as a result, for a certain problem where you have a number of demand points, they obtain the following relationship. They say that the S value that I am looking for is going to be equal to this number. I'm going to write it, okay, plus 2,140 times n. So what is this? They say that given that there are n demand points supported by a DC, the S of the DC, the safety stock order up to level of the DC, is given by this number. So what is the unit of this? This is number of automobiles, actually, or number of units of automobiles. So we have number of units of automobiles here, and this is simply the multiplier of n. So it means that if this DC is supporting, let's say, 25 points, demand points, okay? We don't know the size, let's say average. This is going to be the S value that they are going to have. Well, this is going to be the S value of, let me look at that. I always have problems with this specific, so the following regression relationship between safety stock and number of DCs, number of DCs. So N is the number of DCs, and this is total safety stock in the system. So we are talking about the total safety stock in all of the DCs to support this. So if we have, let's say, 10 DCs, then this is going to be somewhere around 70,000 automobiles all over US as the safety stock, which is not a small number, but I think it might be reasonable. Probably, I think they have done this project for, if I'm not mistaken, for GM or Ford. One of the companies which are now looking for a lot of money. So I don't know which one they use the data for, but I think it's one of them. Okay. Now, So this relation simply tells us that there is a relation between inventory quantity and number of DCs. Now, how are we going to use this linear relation? First, we need to convert this to inventory carrying cost terms. So what they say that, well, the average cost or price of an automobile is $15,000 per auto, and then you have 0.22 or 22% inventory carrying rate. By chance, we have done a project for Tofaş, and they are using 22% as well. Okay, exactly the same number. It's the magic number. Okay, of the companies which are sort of going down. Okay, and so then what we have is we have the total inventory cost, which is going to be this number times 15,000 plus times 0.22, and this is going to be a number like $194 million of inventory carrying cost, plus then I'm going to have this times 15,000 times 0.22, and that part is going to be $7 million, approximately $7 million times N. Now, what does this mean? This means that every time that I'm going to open another DC, I'm going to have an additional cost of $7 million coming in from inventory carrying cost. Now, this is a nice result, of course, but the way that we came to this point is not sort of very clean. But still, I think it is understandable if you are doing an application. Now, once we linearize this relationship, we are doing very fine. Why? Well, now, first of all, this $194 million, we are always going to pay regardless the number of DCs that we open. Of course, this relationship is not valid when you have n is equal to 1. Because when you have n is equal to 0, what does it mean? You are only going to have inventory in the, well, it doesn't mean anything. Okay, so this is only reasonable for values of the DCs that are in between certain region. Okay? It doesn't have any other meaning. So it means that if we are in the correct region, every time that we open a new DC, we are going to have an additional cost of $7 million. So this is going to be at the top of the fixed cost of opening a new warehouse. So this is basically the key. So what we did here up to this point is that we were able to represent the inventory cost as a term which is a function of the number of DCs. Now, once we have that, of course, now we can apply location theory in order to come up with the optimal results. Okay. Now, after this point, I'm going to talk about location problem that is solved. And let me start from here. Now, what they propose is they propose a certain model which is going to take into consideration both service considerations and the location aspects. So they start with the simple fixed charge problem, and then they go ahead to a more integrated problem, which they call, I think they call the integrated model for inventory, transportation, and service quality. Okay, so let's start with the first one. So we are going to see three models. The first one is going to be the location model. This is called the fixed charge model. This is one of the basic models of location, and it has been worked on for probably 40, 50 years. And so what we have is the J is going to stand for candidate sites, and I is going to stand for the I is going to stand for the demand point. And so what we have is, once I define that, we have the following model. We are going to minimize over all j's fj times xj. So minimize fj times xj, where xj, as you can guess, is going to be a binary variable, which is going to take 1 if location j is selected. Plus, we're going to have alpha times summation over all ij, h times, I times, dij times, yij. Now, here in this case, well, I will explain each term one by one. Now, so let me write the model first, subject to summation yij is going to be equal to 1 over all j's for all I. So this is number 1. And I will use this part of the board. We're going to have yij value less than or equal to xj, which means that yij can only take a value of 1 if xj is open. What's the meaning of yij? Yij is the binary variable which represents the case that customer I is served by j. DCJ. So this is only going to be possible if the DC is open. And then we're going to have xj, yij, both binary variables. And so this is more or less the structure. Okay. And so what are the definitions? Fj is the fixed cost of opening. Now note that this fixed cost is going to be the traditional fixed cost, which is the cost related to the land, so on and so forth, plus the 7 million that comes from here. Okay? So in that case, by including that 7 million, you take into account the effect of the inventory cost. And then you have HI is the demand. Dij is the distance in between I and j. I'm not writing it fully, but you can guess. And alpha is cost per unit distance. Unit distance per unit demand. So you might have a cost which is alpha unit per unit times unit. So it is per unit demand. So both of them are in the denominator. Okay. And xj is going to take a value of 1 if j is open, otherwise, and yij is going to be 1 if I is served by j, 0 otherwise. Okay. So again, fj includes the slope of the inventory cost. Okay. So this is actually the solution to a location problem. What this does is it takes into account the transportation costs and now the inventory costs, and it selects the ideal number of DCs. Now, one question, of course, you can ask is as follows. Why don't we include the cost of going from the plant to the DCs? Okay, this is missing here. So this is something that you can think. In other words, we have a cost of going from the plant to the DC, and that cost is, of course, a function of the location of the DCs. Okay, and it's going to be different. Okay, but it's not taken into consideration, and but it might be an important factor. Okay, so this is the first problem. The second problem that they propose is, again, this is a very standard problem, by the way. You are probably familiar with this. Now, the second problem is also a standard problem. It's called the standard coverage problem. So what you aim there is, given a certain number of DCs, you want to cover as much as possible. So that's the coverage problem. So, for example, let's say that we are going to have 10 hospitals here, and we have a blood bank. Where should we locate the hospitals so that we are going to have the maximum coverage? So you can select the location of the hospitals accordingly. It's the same thing is true for an ambulance service. So it's not only in the supply chains that we see, commercial supply chains, but you also have the similar problems in the so-called humanitarian supply chains as well. Okay, so next problem. Let's look at that next problem probably after the break. Okay, any questions? Okay, let's have a break for 10 minutes and then we're going to continue.